School. So this is the setting. So the basic object of study is a positive semidefinite matrix A. So this is an n by n symmetric matrix, and there are several equivalent ways to define it. So one is that all the eigenvalues are non-negative. Equivalently, the quadratic form x transpose AX is always non-negative. And the third is that it can be written as a sum of symmetric rank 1 outer products vi transpose for some vectors vi and Rn. Okay.
You suppose symmetric?
Symmetric, yes. So this is so these. I suppose the matrix is symmetric. I'm only going to talk about symmetric matrices. Okay. So I'm going to. I mean, these are all equivalent, and obviously in the last definition there may be many different ways to write this, but if A can be written in this way, then it has all the other properties. Okay. So I'm going to be interested mostly in this presentation of the matrix. So often a matrix A appears as a sum of outer products. There can be, so if the matrix A is of rank n, there can be, the number of outer products m may be much greater than n. And often there's a natural choice of outer products in which to represent this matrix A, depending on the combinatorial, geometric, or probabilistic, or whatever origin of the matrix. Okay. And so, we think of A as being a mixture of these rank 1 matrices which correspond to projections along certain directions. Okay? And the question which I'm interested in is, can we write A as a short sum of these outer products? So if I give you a sum of m outer products, can I equivalently write this using far fewer terms? Okay? And so one answer to this is given by the spectral theorem. So you can just diagonalize the matrix, and then there are these non-negative weights, the eigenvalues, lambda I, and there are some vectors ui, so that A is some lambda I ui transpose. And there are only n terms in this if the rank is n. And this has, this is very nice because the number of terms is optimal. It's also nice for a bunch of other reasons, obviously, but it's very nice. It's a very compact representation of this matrix. But it has the drawback that these vectors ui, the eigenvectors, in general do not come from the family vi that we already started off with of so-called natural directions. And to see why this is really a problem, let me show you a more concrete example. So suppose I'm interested in finite undirected graphs. So I'm interested in the set of finite undirected graphs G on n vertices. Okay, so one important matrix associated with such a G is a Laplacian matrix, L sub G. This is a symmetric n by n matrix indexed by the vertices of G. And this is a sum of outer products over the edges ij in the graph. The outer products are just ei minus ej transpose, where ei is just a standard vector with a 1 in position I. Okay? And so if I'm interested in suppose I'm interested in the following sparse approximation problem for a graph. So you give me a graph, and it has some Laplacian, and now I want to write this Laplacian as a Laplacian of a graph over far fewer edges. Okay? So suppose I wanted to do this. Well, now it becomes clear why the spectral theorem is sort of useless, because this will allow me to write LG as a sum of n terms, but these terms have nothing to do with edges. These eigenvectors ui are not these. They're not these directions ei minus ej. Okay. So one of the theorems which we proved remedies this, and basically what we showed is that you can always choose your vectors to be vi if you're willing to settle for an approximation. So the theorem is this: given any matrix A of rank n written as a sum of m outer products vi transpose, I can find some non-negative weights si, so that when I look at this matrix A tilde, which is some si vi transpose, it's close to A in the sense that the quadratic form of A tilde is within a constant factor of the quadratic form of A for all real vectors. And at most 4n of the weights Si are non-zero. Okay? So, so the advantage of this is you get the same Vi, you don't have to go to eigenvectors, and also the number of terms, 4n, it's more than the rank, but it's not that much more. It's only a constant times the rank. And it's worth mentioning that there were results in this direction before, and so Rudelson had shown that you can do this with order n log n terms. Okay. So why would you want to prove something like this? Well, I mean, you can apply this in a bunch of different settings and get some nice results. So if I go back to, well, okay, fine. So first, so this is, in case you didn't want to read that carefully, this is just a picture of what this does. You give me a matrix with a bunch of outer products. It kills most of them and gives me some numbers on the rest so that this thing holds, okay? I can get this arbitrarily close to 1. I'll talk about that. I'll talk about that later. So again, if I go back to my world of graphs and apply this theorem there, I get something nice. So you give me a graph G. I look at its Laplacian matrix L sub G, which is the sum of these outer products over the edges. I plug in this theorem, and I get some weights, and the weights correspond to some other graph G tilde. And I know that the Laplacian matrix of G tilde is close to the Laplacian matrix of G by my theorem. And the point is that G tilde has only 4n edges. Okay. So what I've done is, in this picture, you can give me any graph G with up to n squared edges. I can find you a weighted graph now with 4n edges. So it's very, very sparse. So these quadratic forms are close. Now, why do I care about the quadratic form? Well, it encodes a lot of important combinatorial and spectral information about the graph. So, in particular, if I evaluate the quadratic form on any on the characteristic vector of a subset of the vertices S. So, if I pick a subset of the vertices of my graph and look at XS transpose LXS, I simply get the total weight of edges crossing the cut S. So, in particular, if I preserve this quadratic form, I preserve the weights of all cuts in G. Okay, so I have a sparse graph which has the same, essentially the same weights of cuts. And the quadratic form, being sort of the natural notion of energy on a graph, also contains a lot of information about behavior of random walks on the graph and mixing times and spanning trees and things like that. So what this shows is for every graph you can find a sparse weighted graph which preserves all of these properties. Okay. Yeah, so this is what I said earlier. You can go down to O of n edges. Let me just quickly say, I'm not going to say much about the proof, but here are 3 important features of the proof. So the first is that it's iterative. So the way you find these weights Si is you pick them one at a time. So you take something like 4n steps, and in every step you pick some weight Si, and it does something to the spectrum of the matrix that you have, and you have some notion of steady progress. And after 4n steps, you can show that you're done. The proof is elementary, so it uses only basic linear algebra. It doesn't use anything fancy at all. And it's constructive, so it doesn't use any randomness, and it runs in n to the 4th time. And this picture is all I'm really going to hint at about what's going on in the proof. So this is a picture of sort of what our notion of progress is and what our notion of the quality of eigenvalues of a matrix is. It's something like, so if I have a matrix A with some eigenvalues, there are these blue ovals on the real line. I want them to fall in a certain range, and the way I'm going to do that is by putting some real number here, L, and looking at the essentially looking at the sum of reciprocal distances from L. So this is something like taking the Stieltjes transform of this discrete distribution of the eigenvalues at a particular, just looking at it at a particular point. And this is, I'm roughly going to use the fact that this, this potential is, bounded and has some other properties, and this is roughly what we use in an induction hypothesis to do this. Okay. So I won't say anything more about the proof, but there are a bunch of open problems that this suggests, and I'm going to work on them. I've been working on them, and I hope to work on them while I'm here. And so the first one concerns the quality of approximation obtained by our theorem. So actually, we're able to prove the following somewhat stronger theorem. Oh, so okay. So this is, by the way, I didn't prove this myself. This is joint work with Josh Batson and Dan Spielman. So actually, our theorem is you give me any matrix A with written as sum of m outer products. I can find some A tilde with at most dn of these outer products, and this approximation ratio is d plus or minus 2 squared or d minus 1. So why is this number significant? So there's a well-known result of Lubatsky, Philip Sarnak, and Margulis, which says that if you give me the complete graph and you want to find a sparse graph which approximates it spectrally, this number is the best you can do. So, and these graphs are known as Ramanujan graphs. And so our result shows that you can do this with dn terms in the sum, which corresponds to a graph of average degree 2D. And the Ramanujan graph bound is for a regular graph of degree d. So we're a factor of 2 away from the optimal bound. So this is a question, is this factor of 2 necessary? And obviously, I mean, there's also a much more important thing going on. We produce graphs which are weighted, and the Ramanujan graphs are unweighted and they're regular. So you also have to, I mean, if you really want to get actual Ramanujan graphs out of this, you need to get some control on the weights SI. So this corresponds to proving some stronger version of the theorem for the special case when the matrix A is the Laplacian of the complete graph on n vertices. Another strengthening of this concerns getting better control on the weights in sort of more general scenarios. So suppose now I'm given a decomposition of the identity. So I have identity written as a sum of outer products vi transpose, and I have the additional condition that the norms of these vectors are bounded by some constant delta. So then, can I produce weights that are either 0 or 1? So they're not allowed to be just any real number now. Can I produce weights that are 0 or 1? So that when I take a tilde equal to some vi transpose for just some subset of my vi, this thing has eigenvalues bounded away from 0 and 1. Okay. So this is actually equivalent to this old conjecture called the Paving conjecture or the Cadison-Singer conjecture. This is one of the central conjectures in operator theory, and I mean, you can try some approach to this based on our construction. I mean, I'm not anywhere near getting it to work, but at the least it shows that getting very good control on the weights is very difficult. So this conjecture is like 60 years old, and there's it's 60, yeah. 60. So, well, okay, this formulation of it is about 6 years old. There's a formulation of it that's 60 years old that's equivalent, but yes. Here's another thing. So if you apply this theorem to the class of Laplacian matrices of graphs, it actually is the following statement about polynomials. So if you give me an n-variate polynomial of this form, so some aij xi minus xj squared, where aij are non-negative, then I can produce weights bij, which are sparse. So at most, say, order n of them are non-zero, for which these polynomials are closed pointwise for all real vectors. So one thing you could think about is, does anything like this work for powers greater than 2? So what if I have cubes that are power 4 or something like that? So this was suggested to me by Asaf Naor, who had some other motivation for doing it, but I think it's a natural question. And among other things, as soon as you change the power, you lose linear algebra completely. So yeah, so I don't even know if it's possible. I mean, it's not clear if what's going on is very specific to.
Expanders do it, right?
Huh?
Expanders basically do something like
Yes. So yes. So expanders, in the case when this thing is an expander, this is true. You can do it for every p. But I want to do this for general weights, aij.
But so this suggests that every positive polynomial is the sum of squares. So if you have a polynomial which is positive on the real line, you want to write it approximated by a sum of small numbers.
Yeah, you could do that. If this
works for any polynomial.
This works for only for polynomials of this form. But yeah, but then you can if you want, yeah, you can reduce other polynomials to this and just plug it in. Okay, so more computational question is, so currently this algorithm takes n to the 4th time. If you want to use this to speed things up, so there's a lot of papers in computer science about speeding up computations by turning some dense object into some sparse object. If you really want this to be useful for really efficient algorithms on very large graphs, you want this to run in time nearly linear in m, which is the number of edges or the number of outer products. So there's a big gap between mn cubed and m, but can some improvement be made? I mean, if you could get anywhere near here, you could probably use this to get more efficient algorithms for solving linear equations in Laplacian. So this was the original motivation of Spielman and Tang, who came up with this notion of approximation in the first place, because they wanted fast algorithms for solving linear equations. And the last wait, whatever. Yeah, here we are. The last slide, which is this is very speculative, is can use the methods that we use to obtain control on the spectra of these matrices for constructing other interesting matrices. So there's this field called compressed sensing where you're interested in these restricted isometry property matrices, and roughly this is just it's an R by N matrix where R is much less than N, so it's a really fat matrix, and you want all the k column submatrices to be well conditioned. Okay, so you want this matrix to not shrink or expand sparse vectors very much. And so currently the only known constructions of this are randomized, and since our method is deterministic, there's some possibility you could use something related to construct these things deterministically. And there's another very related question called this Gaussian subspace question. So it's known that if you look at L1 and you in n dimensions, that you can there are subspaces of dimension n over 2 which are isomorphic to L2. And in fact, random subspaces have this property, but nobody knows how to get it deterministically. So again, this comes down to constructing some matrix with some properties, some spectral properties. And I mean, I have not thought about this carefully, but this is very speculative. Maybe you can make some progress on this also. So that's it.